All right, today we're jumping into a real classic, a problem from a book that's given physics students nightmares for decades, i.e. Irodov's Problems in General Physics. We're going to break down problem 1.143 step by step so you can see it's not so scary after all.
So, here's the setup. You've got a simple pulley, two masses, M1 and M2, hanging off it. And we get to ignore things like the pulley's mass and friction, which is nice. Now, at first glance, this looks like your standard Atwood machine problem from Physics 101, right? But here's the catch. The question isn't asking for the acceleration of the masses. It wants the acceleration of the center of inertia for the whole system. That little twist is what makes this a fantastic problem.
So here's our game plan. First, we'll do a quick review of the classic pulley problem. Then we'll get into the real heart of it, this whole center of inertia business. After that, we'll figure out the acceleration for each mass, use that to find the system's acceleration, and finally, we'll do a sanity check to make sure our answer actually makes sense. Ready?
Okay, first things first, let's just make sure we're all on the same page with the basic setup, the good old Atwood machine. Before we can tackle the main question, we've got to have the fundamentals down cold.
Yep, this is your textbook Atwood machine. It's an absolutely perfect example for practicing Newton's second law. F equals ma. It's a great little system because the motion of one block is totally dependent on the motion of the other. That string basically ties their fates together.
And now for the twist. The center of inertia. This is what the problem is really about. We're not just looking at how the individual blocks move up and down, we want to know how the balance point of the entire system is accelerating.
So what even is this center of inertia, or center of mass? Well, the easiest way to think about it is as the system's balance point. It's just a weighted average of the positions of all the masses. You can see from the formula that the heavier mass has a bigger say in where that balance point is located, which makes total sense.
Okay, so if we want to find the acceleration of that balance point, the formula looks pretty similar. It's just the weighted average of the individual accelerations, W1 and W2, but, and this is the most important part of the entire problem, you have to remember that these accelerations are vectors. They have magnitude and direction, and if you forget that, you're going to have a bad time.
All right, section 3. Before we can find the acceleration of the whole system, we need to figure out the acceleration of the individual parts. So it's time to roll up our sleeves and do some classic force analysis.
And we're going to follow the tried and true three-step recipe. First, we'll draw our free body diagrams to see all the forces. Second, we'll use F equals ma to write an equation for each mass. And third, we'll solve those equations to find our acceleration a. Simple as that.
Let's just assume for a second that M1 is heavier than M2. For M1, you've got gravity, M1g pulling down, and the tension from the string, T, pulling up. Since it's going to accelerate down, let's just call the downward direction positive for this mass. That gives us our first equation, M1g minus T equals M1a. Now for M2, that same tension T is pulling it up, so its equation is T minus M2g equals M2a. Okay, listen up, because this is a huge pitfall. So many students get tripped up by mixing up the signs. You have to remember, acceleration is a vector. If M1 is accelerating down, M2 has to be accelerating up. Same magnitude, opposite directions. You've got to be super consistent with your coordinate system, or it'll all fall apart.
Now for the fun part. We just have to solve those two equations. Here's a little trick. If you just add the two equations together, the tension, T, conveniently cancels out. And when you do a little algebra, you get this beautiful, classic result for the acceleration. If you've ever studied an Atwood machine, this should look very familiar.
All right, this is the moment we've been building towards. We have the acceleration for the individual masses. We have the formula for the center of inertia's acceleration. We have all the puzzle pieces. It's time to put them together. Okay, let's go back to our main formula. To deal with the vectors, we need one coordinate system for the whole problem. Let's just decide that the downward direction is positive. Now, since M1 is our heavier mass and it goes down, its acceleration, W1, is just positive a. But M2 accelerates up, which is in the negative direction, so its acceleration, W2, has to be negative a. See? Those signs are everything.
So when we plug those values, plus a and minus a, back into our main formula, we can factor out the a and get this expression right here. We're so close. The last step is to just take that formula for a we found earlier and plug it right in.
And there it is, our final answer. The acceleration of the center of inertia is g times the square of that mass ratio. And look at that term is squared. That's the really cool insight here. Because it's squared, the answer is always positive or zero. And since we said down was positive, that means the system's center of mass can only accelerate downwards, or not at all. It can never accelerate up. How cool is that?
You know, getting an equation is great, but in physics, you're not really done until you ask yourself, does this answer actually make sense? So let's run a couple of quick sanity checks to see if our formula holds up to reality.
Okay, first test. What if the masses are exactly the same? What do you think should happen?
Well, if we plug m1 equals m2 into our formula, that numerator becomes 0. 0 squared is still 0, so the whole acceleration becomes 0. And that is exactly what should happen. If the masses are balanced, the system just sits there, perfectly still. The center of inertia doesn't accelerate. Check 1, pass.
All right, let's try an extreme case. What if one of the masses just wasn't there? Let's say we set m2 equal to 0. If we put m2 equals 0 into our formula, the term in the brackets becomes m1 divided by m1, which is just 1. 1 squared is 1, so the whole thing simplifies down to WC equals G. And that makes perfect sense. If m2 is gone, our system is just a single mass, m1, in free fall. Our formula works even in these weird extreme cases. That's when you know you've got a really solid answer.
And that's how you solve it. But, you know, like any good physics problem, finding the answer just leads to more questions. We assumed a perfect, massless pulley and no friction. But what if the pulley had mass and it could rotate? What if there was friction? How would that change the acceleration of the center of inertia? That's a fantastic question to chew on.